Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my first video in a series about probability and statistics. And today I'm going to talk about kind of the basics of probability theory, namely probability spaces. So that's kind of the starting point. And so, what is a probability space? This is the technical definition. This is kind of the broad definition of probability space. This probably looks pretty complicated, but you start with a sample space, and that's really just a set. And any non-empty set can count as a sample space, and the elements of this set are called events. So you have a set of consisting of a bunch of events, and I guess they call that a sigma algebra. I don't even know what that means. It's something in topology. You don't have to worry about that, but yeah, so the sample space consists of a set of events, and each event has a probability associated with it. They talk about a probability measure. And again, this is a very technical definition. But the probabilities of these events in your probability space have to satisfy certain rules. And I'll get to that in a minute. So like I said, the first thing is a sample space. And it's probably a good idea to look at some simple examples of sample spaces. So a very simple example would be tossing fair coin. And I guess the example here is they're tossing a fair coin twice, or maybe they're tossing two fair coins, kind of the same thing. So there's four possible events when you're tossing two coins, right? They can both land on heads, they can both land on tails, or the first one can land on heads, the second on tails, or the other way around. First can land on tails, second on heads. So this is your probability space, just these four events. And this doesn't say anything about the probability. If they're fair coins, of course, we know that the probability of each one landing on heads is 50%, and similarly for tails. So the probability of every event in this space is 25% because you're doing two coins. Each of the four possibilities equally likely. I'll get into that a little bit later, but just the sample space has nothing to do with the probabilities. It's just a space of possible events, and if it's a complete probability space, then all of these events have to together have to correspond to everything possible that can happen. So if these are fair coins, then you know that each coin has to either land on heads or on tails. So the only one of these four things can happen, and nothing else can happen. So that's what makes a probability space. And this is a little bit more of an interesting example, I think. You can also do dice. So the last example involved tossing two coins, but you can also look at the example of rolling two fair dice. They don't even have to be fair for the sample space, but you know that standard die has six sides. It's just a cube, and a cube has six faces. So you know that any of the numbers 1 through 6 can occur for either dice. And here they color the dice. So we're distinguishing the two dice. The first die is green, second die is red. Usually that's not the case when you play dice games. Usually the dice are identical. You don't know which is which kind of makes things a little more interesting, as we'll see. But anyway, that's just another example of a sample space. In this case, there's 36 possibilities. And if they're fair dice, each one has a probability of 1 out of 36. So if you're just tossing one die, then there's six possibilities. So the probability of each possible die roll is 1/6. But anyway, now I want to get in a little bit more about the rules of probability. So, like I said, the probability. So the sample space is just a set of all possible events, but then you've got the probability, which is the measure on the probability space, and the probability of events has to satisfy these five rules. So first, every probability has to be strictly between 0 and 1. An event can't have a probability of 0. That means it's impossible. And that's still, you can have impossible events in a probability space. I haven't really seen it very often, but you can have them. And also, you can have probabilities of 1. These would be events that are certain to happen, like, the sun's are going to rise tomorrow morning, or, a coin will either land on heads or tails, like a tautology. We also call those tautologies. So the tautology in logic is something with a probability of 1. It just means it's certain. And a contradiction in logic is something with a probability of 0, something that's impossible. So those are possible probabilities, and you can have anything in between. Usually, the most interesting probabilities we deal with are something strictly between 0 and 1. And then the second rule says that if you have a sample space, this is what I just said earlier, the probability of everything in the sample space has to equal 1. That just means that something in the sample space, at least one of the events in the sample space has to occur. And then there's a probability involving disjoint events. So you say that the probability of one of two disjoint, so if A and B are disjoint events, then the probability of A or B is just the sum of the probability of A and the probability of B. That should be kind of obvious. Like in the case of tossing a heads or a tails, each of those is 50%, and they're mutually exclusive, so the probability of either a heads or a tails is 1. Um, and maybe a more interesting example, you can think of dice. It doesn't have to add up to 1. You could talk about the probability of rolling a 1 or a 2. Those are both mutually exclusive as well. And you know the probability of rolling 1, if you're only rolling one die, is 1/6. Similarly for rolling a 2. So the probability of rolling a 1 or a 2 is 1/6 plus 1/6, or 1/3. And then there's something called the complement. The complement of an event is just everything that's not an event. It's like every other event in the probability space. And since the complement is mutually exclusive to the original event, and if A is an event and AC its complement is just every other possible event in the probability space, we know that those have to add up to 1. So in other words, probability of the complement of A is 1 minus the probability of A. And then rule 5 says if A and B are independent. This is a pretty important rule, actually. So what independent just means is that say you have event A first, and then you have event B. And a good example is rolling 2 dice. So the roll of the second die is independent of the roll of first die. That means that the second die doesn't care what the first die landed on. If the first die was a 1, second die can still be anything from 1 to 6, and each of those possibilities has probably a 1/6. So A and B are both independent. Let's say A is the event that the green die, the first die, lands on a 3, say. And then B is the event that the second die lands on a 4. Well, you know that each of those probabilities is 1/6. So the joint probability, the probability of A and B, since they're independent events, is the product, P of A times P of B, which is 1/6 times 1/6, or 1/36. So that's what we mean by independent events. And anyway, and here's I think these are the same. Well, actually, there's a few more rules on this slide. So there's a lot of rules of probability theory. I don't know if you want to go all these. Independent, I just went over that one. Probability A and B, that's the same as A intersect B. It's P of A times P of B. If they're dependent, then we have to give what's called a conditional probability. So this is a more general rule. When you have two dependent, they don't even have to be dependent, but just any two events, A and B. Say A and B are two events in a probability space. They could be dependent, they could be independent. In general, it's true that the probability of A and B is equal to the probability of A times the probability of B given A. If you like, that's just a definition of a joint probability. And you can get into Bayesian statistics. If you just kind of invert this first formula, you can get to this bottom equation. This is a very important equation. This is the beginning of Bayes' theorem, this is called. So if you just divide both sides of this first green equation by P of B, you get this very important result known as Bayes' theorem that says the probability of A given B is equal to the probability of A and B divided by the probability of B. And you can also invert it. You can come up with this really interesting results. I'm not going to go into Bayes' theorem or Bayesian statistics today, but you get Bayes' theorem is very important and has a lot of important applications, and I'll get to that more in another video. But and if you have mutually exclusive events, the third green equation here, that just means that they can't both happen at the same time. That means probability of A and B is 0. Like the probability that it'll rain tomorrow and it won't rain tomorrow. It's either going to do one or the other. The probability it's going to do both at the same time is 0. So those are mutually exclusive events. Also like tossing a head and a tail. If you toss a coin, can't land on both heads and tails, so the probability it lands on heads and tails is 0, right? And then uh, and then uh, Yeah, so there's also rules for or, probability of A or B is probability of A plus the probability of B minus the probability of A and B. You can get this from a Venn diagram, by the way. Venn diagrams are a useful way of illustrating probabilities. But anyway, I think that's enough of that slide. And then we haven't really talked about how you calculate a probability. This is kind of a primitive formula for calculating probability. So you say the probability of an event occurring is equal the number of ways it can occur. This isn't quite right. We have to assume that each way it can occur is equally likely. If you have a bunch of ways that are all equally likely for a certain event to occur, you just count the total number of ways it can occur, and then you divide by the total number of possible things that can happen. We're assuming that every possible outcome has the same probability. This is actually a very useful formula because you can. I'll give you some examples of this. So, for instance, say you're rolling two dice. Say you're playing craps. So in craps, you roll two dice, and you really only care about the sum of the values of the two dice. And these are not equally likely. I mean, if you look at the number of ways they can occur, there's only one way you can get two ones. It's called snake eyes. So the probability of snake eyes is pretty small. It's 1 out of 36, a little over 0.02. So it's shown on the right here. And then for three, it's a little higher because there's two ways you can get a three, right? Black die can be a 1, the white die a 2, or the other way around. So that's going to give you a probability of 2 out of 36 or 1 out of 18. I'm just using that formula I showed you, right? Now there's two ways that can occur, and there's a total of 36 possible things that occur. So the probability of rolling a 3 is 2 out of 36. Let's look at 7. That's the most likely one. There's 6 possible ways of getting a 7, right? And so the probability of rolling a 7 is going to be 6 out of 36, which is 1/6. That's why that's the most likely roll. And a little more interesting example, I think, is you can forget about the second column here. This is the payoff. I guess this is a video poker game they're talking about. So just ignore that second column. But these are the 10 possible poker hands. The most unlikely one, the least likely poker hand is a royal flush. And it turns out there's a total of 2,598,960 possible 5 card poker hands. That's just 52 choose 5. I'll get into that later. I'm talking about binomial coefficients now. But just take my word for this. This is the total number of possible poker hands there are. It's a big number. But only 4 of those are royal flushes. Namely, you have to have 10 jack, queen, king, ace, all of the same suit. And since there's only 4 suits, clubs, diamonds, hearts, and spades, there's only 4 possible royal flushes. So the probability of a royal flush is like 4 divided by this big number on the bottom. And they write it as a decimal here. It's like 2 in a million, basically. It's almost impossible. I've never actually seen a royal flush in a card, a live poker game. I've seen a video poker. But straight flush is a little more likely because there's 36 possible straight flushes. So if you look at the numbers in the third column, combinations, these are just the number of possible ways you can get these different hands. And if you divide that number by the total number of possible hands, that'll give you the probability of getting any of these hands, which is the number in the column on the right. So as you can see, junk is the most likely hand. That's basically no hand, like a high card. And that's about 50%, a little over 50% chance you're going to get junk. But the first, I guess, the most likely, what we usually call a poker hand, that's a pair. The probability of getting a pair is about, it turns out to be 42%. So you're pretty likely to get a pair, but then each of these hands gets less and less likely. And as you know, the high hand when you play poker wins. And this column's a little misleading because this assumes that you're just drawing the cards. It doesn't assume that you're discarding. When you discard and you get, when you're finally playing your hand at the end of the game, your probabilities go up considerably. I think probability of a royal flush even after you discard is still pretty low. It's about 1 in 30,000. That's why you practically never see it. But anyway, that's my talk on the basics of probability theory. So anyway, thank you for watching, and long live math, and I'll see you next time.